Hi there, my name is Trent Andrus. I work on high-performance computing and software development for the Ansys Mechanical APDL application, commonly referred to as MAPDL, at Synopsys. In this short talk, I'll cover what software scalability means for MAPDL and what speedup looks like in practice. Why does this matter? Well, maybe you want results faster. Maybe you already have access to an HPC cluster, but your model isn't running faster with more cores. All of this comes back to scalability. Does your job go faster with more resources, and how much faster? Speedup is the baseline metric. Compare the runtime on 1 unit of hardware versus in units. If a job takes 10 hours on 1 core, ideal scaling would be 5 hours on 2 cores and 2.5 hours on 4 cores. That's the theory. Reality is messier, so we need to measure the right things and understand the limits. So how do we measure performance in MAPDL? Well, there are 2 ways. We can use the elapsed or the wall clock time, or we can look at the solution time. The elapsed or wall clock time is the job's time from start to finish, and that's what you experience as a user. The solution time is the solver phase, and this is where most of the parallel work lives. In MAPDL, look for these 2 lines in the output file, the total elapsed time and the elapsed time spent computing solution. The total elapsed time tells you how the whole run behaves, and the solution time is your primary scaling lens. This is the one we focus on. Now, what limits scalability? Well, scalability stalls when the program spends too much time doing communication or synchronization, there's not enough numerical work per core, there's too much serial work, or there's a hardware imbalance, for example, between the CPU, the memory, the disk, or the network interconnects. Software scalability is ultimately governed by Amdahl's law. Simply put, even small serial portions of a program limit speedup. If 1% of the code is serial, the theoretical max speedup, even with an infinite amount of CPU cores, is 100x. And everything outside the equation solver, like reading the model, writing results, or communication, doesn't scale like the pure compute. That's why these curves flatten. The parallel computation part shrinks, and the serial parts become dominant. This is why we focus on the solution phase of the simulation when we talk about scalability. There are other important factors that affect software scalability. The first is what most users care about. This is called strong scaling. Take a fixed model, use more cores, solve it faster. But there's always a ceiling, and small models hit it quickly because you run out of work to distribute. A practical rule of thumb in MAPDL is to maintain roughly 20 to 50,000 elements per core, so each core has enough numerical work. And MAPDL is a tightly coupled MPI application. That means communication can dominate when you use lots of cores, especially across nodes with slower network interconnects. For small models using many cores, you can end up doing more message passing than math, which shows up as poor scaling. And finally, your hardware all works together: CPU, memory bandwidth, network interconnects, storage, and I/O. If you speed up the solver but write results to a very slow disk, the total elapsed time stalls. The solver looks great, but the job doesn't. Balanced hardware matters as much as core count. Here are some practical guidelines for MAPDL. Aim for 20 to 50,000 elements per core to keep the cores busy. Use a big model if you want to use a lot of hardware. Find the trade-off between efficient hardware usage and total time to solution. Keep the system balanced: the CPU, memory bandwidth, the network interconnects, and the storage. And use solution time to judge the solver scaling, while using total elapsed time to judge the user experience for the entire run. In the next 2 slides, we'll look at data for 2 benchmark models. The first model is solved with the sparse direct solver. The second is solved with the PCG iterative solver. Looking at the scaling plots, you'll see 2 common shapes. The first shape is good, near linear scaling over a range of CPU cores until some component, often memory bandwidth or CPU speed, flattens the curve on certain systems. Those certain systems are shown here in this gold oval. The second shape is some speedup that tapers as the model runs out of parallel work or communication and I/O takes over. The point is that models can scale very well, but not indefinitely. These plots and their corresponding data are publicly available on our benchmark website. If you want to read more about these topics, the Mechanical APDL Performance Guide covers solvers, hardware, and in-depth performance details. You can find it in the Mechanical APDL documentation. Also, check out the rest of our HPC video series for discussions on other topics. Thanks for watching.